Previously, we had talked about non-deterministic finite automata, and we talked about a few big deal things. First, we talked about non-determinism. In addition, we also talked about this broader idea that if I give you a non-deterministic finite automaton, NFA, it recognizes some language just like a DFA would. So a natural question is, okay, so what languages are NFA capable of recognizing? Well, last time we established that for any NFA, which, by the way, if it's some NFA called N, its language of that NFA, and suppose I have a DFA, say, as a language D. Those are all the strings for which it accepts. That if I give you any NFA, I can show you how to construct a DFA such that L of D is equal to L of N, and I could also do the same thing in the other direction, meaning that NFAs and DFAs are computationally equivalent. There's an equivalency between the languages that these machines recognize. So that leads me to some natural questions. So first thing, can I add more features in the same spirit as a previous question I had asked some time ago? Can I add more features to the NFA such that, say, on two sides? One, you can imagine I give you the NFA and I want to add some more features so that it doesn't have this relationship. That's one possibility. Another possibility is that I could try to add features to this NFA such that this relationship is generally still preserved. But it makes it easier for us to design a finite state machine or finite automaton such that it recognizes some language. So we're going to be doing the latter here today, and my goal will be to convince you that with these new features for this variant of NFA, that it still will have a corresponding DFA. So the variant of an NFA we're going to talk about here is what was called an Epsilon-NFA. Or in other words, a non-deterministic finite automaton with Epsilon-Transitions. So that brings me to what I want to talk about here. So what feature are we going to be adding here? So this is one possibility of something we could try adding to the NFA. So consider an extension of NFAs where we permit transitions on epsilon. And remember, epsilon is the empty string. So you might ask, what does that even mean? Like what does it mean where it can transition on the empty string? So let me put it in other words for us. Since epsilon consists of no symbols, so the empty string indeed has no symbols, transitions can be made spontaneously. So you got to think back to how these machines operate. So I'm going to keep this at a high level for now. Is you imagine it takes in the string, right? It has a string that it takes in. Say it's string W, and W say is like 0, 1, 1, 1, 0, 0, or something like that. So what it does is it reads one symbol at a time, right? That's what the machine we're used to does. It reads one symbol at a time, it consumes one of the symbols, and it proceeds to the next one. And it finishes execution once it finishes reading or consuming all the symbols of the string, right? So what does this mean in this context then? Well, it means that you can transition without needing to consume a symbol. So meaning, for example, suppose that you transitioned on one of these symbols, and you say we're going to read this 1 next. What we're going to allow to have happen is it's allowed to transition without consuming that symbol 1. But it will eventually have to read the 1. It's just that we're allowed to transition on no symbols. That's what this is all about. So in some sense, it's like if you had say a pet dog, a little puppy dog, and the puppy dog does something for you, and you give the puppy dog a treat. You could still give the puppy dog a treat regardless, right? So perhaps we would like to have it so that the dog doesn't have to do something to get the treat. We just want to give the treat. So this provides some new design features. And I must emphasize these are design features. So this provides some design features. So I thought I'll give you a couple of examples of so-called Epsilon-NFA, which we're going to define after we see the 2 examples. But I think once you get a high-level idea of what this extension does, the definition will flow quite naturally. So let's consider something that we've actually seen how we could do with an NFA, but we can make it actually much easier to do. Let's consider recognizing keywords. So let's revisit the idea of recognizing keywords. So it's a little easier to design with an Epsilon-NFA a machine that recognizes keywords in a much more broader way. Now, there are ways naturally to do it, as we've seen with just an NFA. But let me give you an example of what I'm talking about. So suppose that the alphabet, suppose that we're going to consider strings over the lowercase alphabetical letters of the English language. So suppose that we have this alphabet that all of our strings are going to be over. And suppose that I wanted to detect certain key phrases, just like we've talked about before. So I want to detect, let's try to make it so that we can detect 2 words. Let's try to detect Pam or no. Let's see if we can come up with an Epsilon-NFA that uses this feature. So if we did this with an NFA, it's not very terribly difficult to do this. But the issue at hand is that I would like it to be so it's even easier to do and perform or construct such a machine. So let's do this. So we're going to start off with a start state. I'm just going to numerically label these states, which is a little different than when I usually do this. So sometimes I always like to show you little bits of pieces of things that maybe we haven't seen before. But some people, when there's many transitions that are going to occur, such as over some set, you might want to label, you can also label these over said set. So that just simply means all of the symbols in this set. So this would be A, comma B, comma C, comma all the way up to Z. So on any one of the input symbols here, it's going to transition on to 0 here. However, I would like it so that it can detect Pam or no. So if we were doing this with an NFA, you would have it where you can transition on the P, and you would have it on possibly one goes on the N. However, one thing we have to be careful about when we're doing this is if we have many key phrases, we have to be careful what exactly we would desire. Now, Epsilon-NFAs make this much easier to do. Now, you can, of course, do it with an NFA. It's not too terribly challenging, but it gives you a much more general framework for how you might go about this. So check this out. So we're going to use the same strategy we would be using to detect if the string consists of some key phrase that we're used to from a DFA. So that's the first thing you should notice here. Suppose I have Pam here. I just have a path that reads Pam. Anytime it does not see, say, P on this one, it's just like the thread dying, gets killed, like we talked about with NFA, right? So you can imagine I compose two smaller NFAs, and then I can bring them together, and what I can do is I can use an epsilon transition to get me over here for free. So what do I mean by this? Well, what I'm saying is, if, say, for example, you're reading in the string, you don't have to actually read a symbol to get to state 1. So you're going to see that this actually has a natural mechanism, which is referred to as an epsilon closure, which I'm going to define when we talk about the formal definition of computing for an epsilon NFA. It essentially allows us to be in state 0 and state 1 freely, right? Like, because I can just go here for free, right? I don't have to consume the symbol. I don't have to read the symbol directly. I just read the empty string. So it means that I can be over here, allowing a thread or continual guesses to produce here, but I could freely go to state 1 at any time from here. So for example, the minute I see a P, I can be in state 1 and I can read Pam, if Pam was indeed the sequence that came. But this also is a nice pattern because now I can add more states and use the same strategy. So say if I want to have it now, or I want to read no, right? Well, what can I do? Well, I don't have to add anything special here, except for an epsilon transition. But there's something I haven't quite done. Remember, as soon as I detect Pam, I'm going to have it where I just see those strings. But do you notice here that, so I would like to be able to detect if these strings are present. But the thing is, I'm just putting in the context for which if you're typing in a sequence here, if I wanted to allow there to be more symbols, I would design this NFA a little bit differently. But do you see how I can use these epsilon transitions just to have it where if I want to have more keywords, it's just an epsilon transition and a pathway like this. What this one would do is it would detect if Pam or no is the most recently typed string of symbols. Say if you're typing in this on a keyboard. Or in other words, the string ends with Pam or no. Exactly, Miss Kitty. Exactly. So this is an example of one application. Let's consider another one. So you can actually use the epsilon NFA to simplify the design process for detecting key phrases. And you can pick up all of the stuff that you're familiar with from NFAs to augment, say, for example, this epsilon NFA. So, for example, if you wanted to have it, where it just contains Pam or no, you can easily pick up the strategies that we've seen before. However, here it's just simply if Pam or no is at the end of the string, because we're looking at what's most recently typed. Let's consider another example. So we might want to consider, and this is a nice classic example, is say you want to have a machine that's for reading decimals. Right? There's many machines that you want to read decimals on, like say you can even think of something like a calculator, right? Suppose I want to read some decimals. So I'm going to give you an epsilon NFA that's going to be capable of doing the following. So I'm going to give you some specifications. Below is a epsilon NFA. What's an epsilon NFA that accepts decimal numbers with the following format. The following format. So what we're going to have is the string is always going to have a particular form to it. The first thing is it's going to have an optional plus or minus sign. So it can be positive or negative. It may have a string of digits. Then I'll have a decimal point, potentially, right? And it may have another string of digits, right? Another string of digits. Note that that if we want to have it where we want to have it, where it's a string of digits and another string of digits, this decimal point has to be present, right? But note that we just don't put a decimal, right? We have to have at least one. We have to at least. Let me just make a note about this. Note that it must be that one of 2 or 4. So this string of digits or this other string of digits must contain at least one digit. I.e., the string must be non-empty. That's another way of me putting this. So the string must be non-empty. That's a really funny word right there. It looks like the string sort of melted into itself like cheese. So we're going to design an epsilon NFA that has all of these features. So it's able to accept any decimal number written out as a string in the following form. So let's try drawing this out. So let's try to come up with something that follows these rules. So we're going to have Q0. It's going to be our start state. Now, as an optional plus or minus sign, so the minute you hear optional, you might suggest to use an epsilon transition, right? Because it's just like if I have the puppy dog, I can give the puppy dog a treat, or the puppy dog might want to do a trick, and it gets the treat. So if you're leeway like that, this sounds like an option, right? So let's do that. So let's have it where it has an epsilon transition. It can read a plus or a minus, but only one of these, right? And then it takes us to a state we're going to call Q1. Now, once it's at this stage, it's supposed to take in a string of digits. So that means it could be a 0, could be a 1, could be a 2, could be all the way up to 9, right? So just keep in mind that the reason why we're including 0 in here is it's just padding on everything, right? It's just like if you had a whole bunch of zeros sitting out in front. But if you don't like that, we can... Actually, we'll keep it like this. But if you don't like this epsilon NFA, I encourage you to think about how you would have it such that you forbid this in the design. Notice here I don't have anything that says that we're not allowed to have a 0 sitting out front like this. So we have a decimal point. So upon having a decimal point, it has to be that if you get a decimal point, there has to be another string of numbers that come after it, right? Because in this case, it could be the case that you just go right to the decimal point, right? But that means that there's going to be at least one digit. So we're going to have 0, 1, all the way up to 9. Any one of these symbols would suffice. And then on Q3, we can read in some more symbols. However, another possibility is as follows. it could be the case, because remember, notice it says, note that it must be that one of 2 or 4 must contain at least 1 digit. So in this case, notice that it doesn't require there to be a digit before, right? But it requires it after the decimal. I want to make sure that there's a case for which we guarantee that there is at least 1 digit before the decimal point. Then we transition on the decimal. And now, upon reading any more, we'll have it on epsilon transition. And finally, let it accept. But notice that I'm using the epsilon transition here to optionally allow me to get to the final or accepting state. I'm not using it in a way that's just like, it's just now it's an option to say, do you want to stop? So this is actually another helpful feature of having the epsilon transition, is if I'm reading in more stuff, the epsilon transition allows me to freely go over to the accepting state without having to read a symbol. Very nice, right? So this gives you a couple different ways you might use the epsilon transitions. In the first case, we want to recognize some keywords. The epsilon transitions make it easier to design it such that you have certain target strings. That maybe, for example, what we had was you look for it as the most recently typed sequence or the end of the string, versus here we might use it to represent options, such as in the case for which I want to put something at the beginning of the string, or I may want to have it where I allow it to freely go to the accepting state if, say, there's nothing else. So if I have nothing else to read, I can allow it to just freely go to the accepting state, because once it gets over here, it can read any symbols you want, and it's good enough. So that brings me to defining what an epsilon NFA is. So hopefully you understand the main idea here. So the feature is that we allow it to transition even when it doesn't read a symbol. So it gives us effectively what amounts to an option. Which you can use in many different ways. So let's consider now the definition of a non-deterministic finite automaton. A non-deterministic finite automaton with epsilon transitions. So this is abbreviated as an epsilon NFA. And I'll usually refer to it in that sense, but this is the full name. And yes, that is terribly straight. So let's proceed. So I'm going to keep the definition as brief as I can about this, at least for our presentation here. I'm going to presume you know what an NFA is, because the definition is nearly identical with one major difference. A epsilon NFA E is a 5-tuple. Q sigma, which is so this is our set of states, the input symbols, delta is the transition function, Q0 is the start state, and F is the set of final states, where everything is as in NFA, except we allow the transition function to behave a little differently. So here's how we're going to formally define this, and I'll explain it in plain words here. So it's going to look not that much different. So delta is going to be defined as follows. So it takes in a state and an input symbol, or, so this is together here, so, or epsilon. So now I've introduced epsilon into what can be the string here for the second input for the transition function. Please note that epsilon is not a part of the input symbols. It is not. and it outputs a subset of the states. So some member of the power set of the states, so any subset of them. So it gives you a subset of the set of states. So in plain language, so this is a state. So given a state, given an input symbol, or epsilon, it gives you a subset of the states. So this part right here is the only part that differs. So please remember, so I'm going to make a remark about this. Epsilon does not belong to the set of input symbols. Yes, Miss Kitty, I haven't forgotten. That's why we're writing this. The set of input symbols, sigma, it is a feature of the NFA, of the epsilon NFA. So notice there's nothing too terribly surprising about this definition. It allows it so that the transition function can now transition on epsilon, meaning it doesn't have to consume a symbol. That's an epsilon NFA. Do you have any questions, Miss Kitty? You don't? You don't? That's awfully nice of you. As long as you behave yourself, okay?